In the last video, we were talking about dark matter, and I, of course, ran out of my 15 minutes. All right, so I'm going to just continue this. So when you use the modified version of Kepler's third law, let me go to the next slide, and this really shows, the experimental evidence that shows that dark matter is there. Okay, so let's take it doesn't have to be our galaxy, it could be really just any galaxy shows this evidence. But if all the matter is what is visible, like what's emitting radiation, then with this particular model right here, the further you go out from the center, the slower the stars should be orbiting. As you go farther and farther from the center, you're farther from most of the mass, and so these stars way out here at the very tips of the spiral arms should be traveling much slower. And if you just kind of think about that for a second, like take the model of just our solar system. The sun has the vast majority of the mass in our solar system. I mean, the planets have some mass, but it's almost insignificant compared to the sun. And so the sun really controls the speed and the orbits of the planets. So of course, Mercury, being the closest to the sun, travels the fastest, and then it gets slower and slower as you go further out. Once you get to Neptune, Neptune is traveling the slowest of them all. And then, of course, you can go beyond Neptune, not even considering planets. I mean, just objects that orbit the sun, like, for example, Pluto or, other Kuiper Belt objects are moving much slower, even slower than Neptune. So it's really just how far the object is from where the center of mass is, and so this is from what is observed. This is what we would expect. We'd expect the speed of these stars way out here to drastically drop off, because there's just no mass, or there's no visible mass out there. But that's not what's observed, right? Back in the 1970s, we observed the fact that these stars way out here are traveling at very high speeds, and so the explanation, the only way that we can come up with why they're traveling at this speed. I mean, lots of ideas were tried and rejected for various reasons, but there must be some mass way out here in the halo around the galaxy, enough mass to keep these stars traveling at these speeds. Speeds that you'd expect, much closer to the center of the galaxy. So this dark matter causes those stars to travel at much faster velocities than than can be accounted for by the mass that's observed. All right, so so that's why there's dark matter. Okay, that's why we this evidence shows. And this is called a rotation curve. I don't think I said that yet. This is called the rotation curve, and like I said, this is very typical that we see with all galaxies, right? They all have this dark matter around them, and we really don't know what it is. There's been lots of ideas trying to figure out what dark matter is, and it's really a central idea or a central question in 21st century astrophysics. What is the dark matter? And that's someday hopefully we'll figure that out. All right, here's some different. There's different dark matter candidates. There's actually two big ones. Like um, one are called machos, and these are massive objects. And then the other one is called WIMPs. These are weakly interactive massive particles. Um, I mean, if you're really interested in that kind of stuff, you can read about it. It actually has more to do with what's called particle physics. Subatomic physics, and what's going on in the subatomic world, if you will. Of course, that does. I mean, atoms ultimately are the building blocks of things like planets and stars, and why not dark matter? The thing is the problem with that is what we know about matter is when it heats up, it emits radiation, and we always see that. I mean, we've never not seen that, and so. What is this dark matter? It really is just a big question. I mean, these are just guesses. These what are called machos and WIMPs. I don't know. I don't know what like I said, I don't really know. No one does. All right, so let's turn to what are called active galaxies. This accounts for about 10% of the galaxies that we observe in the universe. There's really three types I really want to talk about: radio galaxies, Seyfert galaxies, and quasars. There are other types, other categories, but those are the three main ones. Let me just say that there is, if you hear the word, or if you hear the term active galaxy, that's also referred to as an AGN, which is called an active galactic nuclei. All right, so that's that is just another name that these things go by. And actually, this is more descriptive than just simply active galaxy. As you'll see, that there's a reason we call them AGNs, and it has to do with what the source of these active galaxies are. All right, so let's examine them in a little bit more detail. There's lots of things to learn about these different types of active galaxies. The main thing I'd like you to know is that mostly, not 100% of the time, but mostly when you find radio galaxies, you're talking about an elliptical galaxy. That, like I said, that's not always the case. So what makes them radio galaxies is they're emitting tremendous amounts of radiation in the radio region. Compare that, like, for example, the Milky Way, right? Our galaxy, or Andromeda, which is, the next large spiral galaxy. And by the way, these things don't, the active galaxies can be spiral, they can be elliptical. But those are two good examples of just normal galaxies, right? Not active galaxies. And so the Milky Way, produces, of course, and so does Andromeda, produces a certain amount of radiation in the radio region, but not nearly as much as these radio galaxies. They're producing tremendous amounts, yeah, that's the main thing. Is just remember, radio galaxies tend to be elliptical galaxies, and of course they're emitting a great deal of radio energy. All right, and they seem to be small. We'll talk more about this. The idea that is the source that varies is less than a light month. Like, if you think about it, the distance that light travels in roughly 30 days or so, these things seem to be smaller than that, because when they vary the radio radiation, the variation takes less than a month to vary. So that tells us that the size is less than a light month across. There's a nice picture that will explain that in a little bit more detail. And the other thing, I guess the other thing that is very prevalent in these radio galaxies is we can observe these large lobes, these radio lobes that are emitted. They're not always symmetric like this picture is showing, but there's usually these huge amounts of radiation emanating from the galaxy itself. These are associated with what are called jets, physical material that is leaving the galaxy, usually in the directions of magnetic fields. All right, so let's move on to safer galaxies. Again, these are active galaxies. They're producing more energy. And the thing that I would like you to remember about safer galaxies is they tend to be spiral galaxies. All right, if it's a spiral galaxy, there's an active galaxy. It's generally classified as a safer galaxy. All right, and there's lots more information. The one thing that's common, of course, with radio galaxies is the region of energy is coming from a really small region, and I'm kind of giving away the fact that I'm pointing at the nucleus, and of course remember the name of active galaxies, the other name, active galactic nuclei, right? So it's really associated with the center of these galaxies. So what could be at the center of these galaxies that's causing them to be active? All right, so that's the big question that I want you to be thinking about, and we're going to answer that, of course. All right, and the last category of active galaxies, and like I said, there are other ones, but the last of the three general categories, radio, safer, and quasars. Now, quasars actually have a little bit of history. They started, people started observing these things back in the 1960s. And when astronomers first looked at quasars, they noticed that the redshifts. So remember, that's where the spectral lines of, let's say, hydrogen are. They seem to be shifted enormously to the red end of the spectrum, which means that these things are traveling really, really fast. So they're either, and the reason they're called quasars, that stands for quasi-stellar, let me think, quasi-stellar, anyhow, they weren't sure whether these were stars or, really distant galaxies. And of course, that's, the latter is what they turned out to be, were they back in the 1960s? They were asking themselves, what were these redshifts caused by just really fast moving stars within our galaxy, or were they enormously distant objects, and they were just the nucleus of very, very distant galaxies, and that happened to be very, very energetic. They're pouring out more energy. All right, so these things, like, this is a good example. So this tells you something about, how do we distinguish between, like, an active galaxy? So these things are about 1,000 times more luminous than, like, our galaxy, our average normal output of energy, the Milky Way galaxy. So active galaxies, including quasars, of course, tend to be 1,000 times more, plus or minus a little bit there, but they're very energetic, and so it's and again, it's just 10% of the galaxies that are out there. When we go and we look out into the universe, and we find these active, AGNs or active galactic nuclei. All right, looks like I'm running out of time. I'll start.